Okay, thank you very much. I'm done. No, I guess I have more to do. Okay, so let's get on with it. I'm going to talk to you about 3 different parts. I'm going to give you a little bit of a review in fiber very quickly, just to give you a feeling for what the complexities are down there. Talk a little bit about WDM systems, and then close with IP over WDM, both pointing out a couple of key issues as well as showing you some real-world experience that we've had. So the first thing to say about fiber is I've not got my screen set up right. Is there a tech person? I've got half a screen.
This laptop set to 1024 by 768.
It's a different you made me test this last night.
Go for it. It'll take me longer than it gives to give the talk. Go all the way down to
I don't have any problems on it.
Hello, Stan.
San Francisco. Many thanks. Well, although that was a digital problem, the message to you when you enter the fiber world in transmission is that it's an analog problem. It's always been an analog problem. It continues to be an analog problem. And the major consequence of it being an analog problem is that it's very difficult to have mid-span meet, as we talked about with Sonnet last time. Today's setup is that every single WDM system does it differently at the physical layer, down at the analog problem. And you can't plug vendor A into vendor B. And I personally feel it'll be quite some time before you ever have a chance to do that. So let's talk a little bit about what are the issues at this analog level of the world. Well, it's attenuation, dispersion, nonlinearity, and reflectance is basically the issues. So let me show you what a few of those are. If you look at a piece of fiber, of course, it's this long piece of glass, but it doesn't transmit at all windows equally. So you've probably been exposed to the 1550 window and the 1310 window. This is the absorption curve for fiber, and those 2 windows come about for very physical reasons, that water molecules in glass cause this big spike, and there turns out to be 2 good regions to work at. Now, for long distance, where I'm going to focus, the preferred choice is always in the 1550 window because it's about half the attenuation that you get at 1310. And also, as you'll see, at this window, a thing came along called the optical amplifier that really changed the way we put the networks together. The other important part to know about fiber is, in addition to from a mathematical point of view, the real part, which is the attenuation, there's the imaginary part, or the dispersion. These lines are the velocity, if you will, of different wavelengths of light. And it is not the same for all wavelengths. And there's 2 kinds of fibers. This is the original fiber that 80 or 90% of the world is full of, called standard dispersion, non-dispersion shifted fiber. And then when people started working in the 1550 range, they went to this kind of fiber, which was either dispersion shifted originally, but then they found that when they turned WDM on in the 1550 range, that dispersion was a good thing. So instead of having non-dispersion shifted fiber, they went to non-zero dispersion shifted fiber, which gives you a small amount of dispersion, but not zero at 1550. So what does this all mean? It's all wonderful, but what it means at the end of the day is that there was a phenomenon called dispersion that happens in the analog transmission of ones and zeros over fiber. You put in nice clean shapes, and at the end of the fiber, you get muck out. And it's frequency dependent. This problem goes up like the square of the bit rate. So for slow speeds, at least in backbone slow speeds, OC3s, OC12s, and for the most part OC48s, dispersion isn't a great issue. But at OC192, where our backbones are going now, suddenly this dispersion problem becomes quite important. There is a number of kinds of dispersion. Another one's called modal dispersion. Instead of having a slope where each frequency travels differently, in multimode fibers there is many modes in the fiber, and they all travel at different speeds. And the reason you never see multimode fiber used in long-haul networks is because the multimode fiber dispersion problem is much more severe with long distance than a single-mode fiber. So that's the last thing I'm going to say about multimode fiber. There's all kinds of problems. I'm going to just show you a couple. Another one that you may have seen come up when people started talking about OC192 systems was a problem called polarization mode dispersion. Even in single mode fiber, there are two polarizations, vertical and horizontal, if you will. And it turns out that there can be an interaction due to a variety of causes, most likely imperfections. Fiber's not really round. And if you go fast enough and far enough, it looks like the vertical, say, is traveling at a different speed than the horizontal, and you end up with a mode that is being dispersed. In other words, the bits are blending together again. And unlike the previous problem of dispersion that was bit rate dependent, this one is a material property. And this is the one that sometimes you hear people talk about, I'd like to use OC192, but my fiber plant won't support it. It's the PMD problem that they're usually referring to. So it's yet another kind of this nonlinear problem, this one dependent upon the fiber plant. And if there's not enough problems, just to show you some more, along comes WDM, which we're going to talk about in a minute. And the issue with WDM was, if there's no dispersion between the wavelengths, as in this case the four primary wavelengths travel down the fiber, they tend to interact with each other, and they create all these different beat signals. Think of it in terms of radios. It's the same thing. It's intermodulation distortion and beat patterns appearing. The problem here with four-wave mixing is that some of these patterns, some of these interference happen to fall exactly on one of the frequencies you're transmitting. So it becomes impossible now to either electrically or optically filter this kind of crosstalk out of the systems. So this is the give and take that the people that design WDM systems have to go through constantly. If we increase the bit rate, we have more problems with chromatic dispersion. If we lower our dispersion on the fiber to correct for that problem, we cause four-wave mixing problems, and it's a careful balancing act going back and forth between these three simple nonlinearities and a whole host of others that are carefully balanced at the analog transmission level to make it all work. So my bottom line message there on the couple of slides about fiber is that it's an analog problem. It's fundamentally a proprietary solution to a complex set of different nonlinear interactions. And depending on which vendor's technology you look at for their optical amplifiers or various pieces of their systems, they will choose a different solution. So no two WDM systems are alike in this way. So now let's look at just the basic building blocks of what WDM is. Well, to give it a historical perspective, we wouldn't be talking about WDM if we hadn't come along with an optical amplifier in the earlier days. Around mid-90 to 95, somewhere in there, depending on who you ask, optical amplifiers became commercial. And the king of the optical amplifier is the erbium doped fiber amplifier, known as the EDFA. Before the EDFA, we had systems that were connected. This would be, going back to our sonnet talk, this would be a line set, and these would be sections between pairs of regenerators. And you want to get across the country, every 40 to 80 kilometers, you better have a hole in the ground into which you can put a regenerator that does a full 3R, re-amplify, reshape, and retime regeneration of a single wavelength signal. So then in the early 90s, some bright physicists came up with the ability to make an optical amplifier This amplifier was only a 1R amplifier. It did not do the reshape and retime functions, but it did compensate for attenuation in the fiber plant. And these became very popular, mostly because it turned out you could space them every 120 kilometers. So you had a lot less equipment, and the equipment tended to be a little bit more reliable than a regenerator because its functionality was lower. So the ground was set. This happened in the mid-90s, early 90s to mid-90s, and then it was a fairly simple jump forward. It kind of happened slowly. People tried 1 or 2 waves in the early 90s, but one way of thinking about this picture is what Sienna, for example, brought us, at least the investment community, in the 90s, in 96 when they went public. The idea was we've already stripped out a lot of the regens, and we put in optical amplifiers. Optical amplifiers can amplify all sorts of signals simultaneously. Let's just multiplex at the optical level many different terminals, each on their own wavelengths, into a pipe and send them down the wire, and the optical amplifier will amplify all of them, and we'll sort them out at the far end. So this again was, say, 90. This kind of picture was 92, 93, 94. This was 96 and thereafter. And by the way, the state of the art, I threw 3 terminals here. Think of it in 2 ways. The Sonnet folks tend to put out new Sonnet levels every 3 to 4 years, 4 times faster than the previous level. In WDM, it's not the bit rate, it's the channel count that matters. And from 1990 till now, the channel count has increased from 2 to 128 OC192s on a single fiber, giving you now over a terabit of capacity on a single mode fiber using these DWDM architectures. So I wanted to show you a little bit about the EDFA, since that's really, in my mind, the heart of the technologies that brought WDM to us. It's a device that takes a coma wavelengths in the optical space, so this would be nanometers of light, and this would be amplitude. Send it through the device, and it comes out bigger. All these channels, these are all being modulated. OC48, OC192, the amplifier does not care. It amplifies all of them concurrently, and it does it completely optically. There's a special fiber, the erbium doped fiber, hence the erbium doped fiber amplifier, that has an erbium atom added to it. And without getting into the physics, it's capable of actually, if you pump it with light, that the erbium atoms get excited, and when the signal goes through, they amplify the signal spontaneously. They give the amplification of the signal. So we have a very simple device now that is bit rate independent, and as long as your wavelengths are within the passband of the EDFA, it's channel count independent to a great extent too. So we see now, for example, new amplifiers being offered that will support 160 wavelengths. You start off with 16, 32, whatever you want. Just keep growing your system. You put the fiber in, you put the amplifiers in, and you're good to go until you hit 1 to 2 terabits today. And WDM will probably, I think, in the next couple of years, we'll see 10 terabit systems on a single mode fiber. So what do the WDM systems actually look like? Well, we talked about the amplifiers. The WDM systems are really just optical modulators and a combining system. This is a very simple picture. This would be 1550, 1551 nanometers wavelengths. If I'd been a little bit more careful, what the ITU does is they recommend 100 gigahertz spacing, which is actually 1.6 nanometers. So if I'd drawn this out properly, there is a set of channels that the ITU-T prescribes and everyone is standardized on. These are then combined, sent through up to, I think it's about 800 kilometers is the state of the art, using amplifiers approximately every 100 kilometers. And at the far end, you separate it back out using an optical filter that detects each wavelength and steers each wavelength to the right receiver. So if we look then at what goes on inside the transmitter and receivers, what we have here in this architecture is we have an ODE conversion going on. Usually the signal that's sent to a WDM system is a short reach 1310 Sonnet signal today. That signal is terminated, and it electrically drives generally an external modulator, which means that there is a precise wavelength laser, say 1550 or 1551, that is being driven through the modulator, and the modulation is being applied electrically to that new carrier. So that coming out here is exactly the same electrical signal that went in over here, but it's then converted onto a specific wavelength for multiplexing into the long-haul network. If we come over here then, on this side we have a receiver for the 1550 light. We have a 3R refunction, re-amplify, reshape, and retiming, 3R regeneration, and then a new transmitter, put it out on a short reach link. It's important then to think again about one of the things that Sonnet was so good for was this 3R function. And this 3R function is being folded into the WDM systems. So now if we look at the state of the art, WDM systems have been used at various line rates. Most people generally think that using a wavelength below OC48 is not cost effective, at least in the long haul. So the state of the art today is either OC48 2.5 gig signals or OC192 10 gig signals. And this has been fielded. The 40 lambda system for OC48 is a Sienna system that's been out for a number of years. The 16 wave 192 system, for example, is the Nortel system, which has also been out for a number of years. There is an effort to expand this. The kind of the state of the art of what the people are putting as what will be available shortly is 160 lambdas at 10 gigs, 1.6 terabits of capacity on a single mode fiber. The other thing that's been going on, I'm not going to talk a lot about, is I've shown you WDM as a point-to-point system, but there's certainly a lot of extensions being proposed. One that's been around for a while is the idea that on a long-distance link, why go from just A to B if I could drop some traffic at C and D and places in between A and B? The configurable add-drop multiplexer allows you to drop a wavelength, to sip from the fire hose, if you will. It allows you to get a more complex topology over a limited physical infrastructure. And then, of course, what we're all watching to see this year and next year is the entrance of the metro products. WDM was a tremendous solution for fiber exhaust in the long haul. And the transmission folks are looking to see if they can repeat that performance in the metro area by supplying very versatile transmission systems that will allow you to provision services in metro areas very quickly. It's a little different play than fiber exhaust. Here it's a question of quick provisioning rather than adding capacity where fiber was limited. Okay, well let me move on to the last piece of my talk then, which is just a little bit of experience that we've had at Cisco on how these systems run. First, I'll show you a couple of things. There's 2 points that generally come up when we talk about running IP over WDM. The first one is synchronization. And again, if we think back to the talk we just heard about how synchronization is done in a Sonnet network, it's very different. In a Sonnet network, because it was originally designed to support voice traffic, the whole point was to be able to multiplex many small tributaries up into large trunk lines and to easily demultiplex them at the other end. So we saw a very tight timing synchronization plan to do time slot extraction through the ADMs. Well, that's not the way IP over DWDM tends to get implemented now. When IP over DWDM tends to be implemented as a point-to-point connection to build up either a partial or a full mesh between your router connects. As such, the connections between the routers generally operate with packet over Sonnet technology, which you all also saw a minute ago, and they're direct connections between a backbone router and another backbone router, and there's no Sonnet multiplexing going on here. There's no need for a primary rate source here. Up here in the WDM side, it's a point-to-point link between store and forward type boxes, and therefore there is no timing relationship between the link on this router and any other link in any other part of this network. So there is no need in an IP over DWDM architecture to have to use a Sonnet Stratum-based clocking system. What we do in our products is we relax the clock accuracy to 20 parts per million, which happens to be the very edge of the SONET spec, so that we can bring a low-cost clocking solution that's still SONET compliant, works great over WDM, and if you're using the router to connect your POS links into a SONET network, all we do is we loop time off the stratum clocks that are inside the SONET network to provide us with local clocking. So you have in the router, you have the precision to connect synchronously into a SONET network, but you also have a simpler solution if you want to go straight over WDM, because it's just point-to-point. Another place where there's a lot of discussion going on is the need for optical protection. Again, it's coming about because SONET is being displaced, and as SONET's being displaced, the wonderful 50 milliseconds that SONET had, people are saying, where am I going to get that? My message to this audience is that optical protection is a nice thing. It fixes the cloud generally fast, 50 milliseconds. But it is limited to what's in the cloud. It does not protect the electronics generally in the WDM systems, although sometimes that's part of the cloud. But it certainly doesn't protect anything out here. And sometimes things happen out here. So my message is that layer 3 restoration is required, whether or not you use optical protection. Optical protection is great inside the cloud, but it is not sufficient to give your network end-to-end protection. So, just a couple of slides about the experience we've seen with some of our customers. Here's a situation, a test we performed about a year ago using the Sienna 40 wave system and the GSR 12,000s. We went in on one wavelength, down 500 kilometers of fiber, out, wrapped around, back in, out, back in, round and round and round and round. 20,000 kilometers of transmission, error-free from the first day we plugged the GSR into the sentries, without a single piece of SONET equipment being needed. There's a corollary to this one too, which I don't have a slide for, but we put a press release out recently where a particular customer had some submarine requirements. Plugged the GSR into their transponder system, ran 7,500 kilometers through 150 optical amplifiers, no SONET equipment, worked fine first day, got the ping. It's really pretty easy if you have SONET compliant interfaces. Here's another system we worked with. It's the Nortel 16-wave OC192 system. In this case, the way in is a little different. The way in is because it's configured as a 4-fiber BLSR ring, is through a box that's kind of a combination of DWDM and an add-drop multiplexer rolled into one. My message here was that in this particular product, in the first go, they plugged the GSR in over an OC48 link, and therefore we were multiplexed with 3 other OC48s up to 192 and put out on the ring. That worked fine. Now you want to go to 10 gigs because SONET, Cisco and others will have OC192 soon, this year, late. And gee, there's an issue because this particular vendor doesn't supply a transponder at 10 gigs. You would think, gee, let's put the colored laser on our box and we're done. Think again of those earlier slides I showed you of all the complexity. It's not that simple. I think Nortel has now put out a transponder that allows you to plug in. But the lesson is that the passive systems are difficult to plug into because of the analog complexities of WDM transmission. Finally, what have we got? Well, I've argued a few times now that transmission's an analog problem and it's proprietary by nature. DWDM provides tremendous capacity, and if you use transponders, it really is an open architecture that's very flexible. We have done a large number of large deployments around the world at this point over most everybody's WDM equipment, and it generally works pretty well. So this is not a future. IP over DWDM is quite doable and a reality today. Thank you.
Time for a question. Time for. Let's see. Time for a question or two.
Questions? Yeah, if you want to go up to the mic. You talked about layer 3 protection. Could you go up to the mic? It's not that far.
You talked about layer 3 protection. How long do you think it would take for discovery and failover time compared to
I'm sorry, you asked about protection?
Right, layer 3 protection.
Layer 3 protection. Right. Well, you can't compare it to, well, how shall I answer this? You're going to see a talk from this gentleman, I think, in a minute, on DPT, which is a solution that provides 50 millisecond protection for direct router-to-router connections. But it's kind of still physical layer. The reality is that the restoration at layer 3 is fundamentally more complex than protection at layer 1. And I think what we're looking for is something that's fast enough to support real-time services. I guess it's a sub-second, but it may not get all the way to 50 milliseconds. We're certainly looking for input on what the right choice should be.
I have a question. I'm quite confused by your presentation. I'm actually from the optical research. I have the background. Well, my impression is you are using SONET framing, and you have your SONET gear built into your router and Sienna's add and drop in your router. And but you can't call yourself SONET compliant because you don't have the clock precision.
The question was, we have some SONET, but is it fair to say it's SONET compliant? It is SONET compliant in the sense that it complies with GR253 and the ANSI specs and the ITU specs. It is not, so it is compliant SONET signal in all senses. But what it is it's a concatenated SONET stream where we statistically multiplex packets. There is no notion of virtual tributaries or circuits inside that SONET frame. So we don't do what an ADM does, but we're just as compliant at the signaling level as any ADM. That's why we plug into the WDM system so easily.
Yeah, thanks. That's my impression. You're not using an analog system. You're using SONET framing and a lot of the SONET things there. And it's not that as dramatic as you describe its analog technology. It's not.
I'm not quite sure what your point is, but it certainly is analog technology, and it certainly is proprietary.
But if you have SONET framing, you have SONET there. It's digital.